Hello everyone. My name is Dipanshu, and today I'm going to talk about sequential decomposition of graphon mean field games. And this is joint work with Rajesh Mishra and Sriram Vishwanath. There are a lot of real world examples where there are a large number of selfish players who interact with each other through a networked game. Such examples include, for example, online platforms such as Lyft, Uber, and Airbnb, where there are multiple parties on both sides, either offering the service, for example, offering Uber or Lyft service, the drivers, or the passengers. Similarly, there could be cyber physical system. In cyber physical system, there could be a large number of nodes who are making some sort of measurement and they're interacting with each other. In renewable energy markets, there could be wind producers and solar energy producers and consumers on the other side who are again interlinked through a market. And all of these agents are strategic in nature. They are connected to each other through a network, and they are selfish, which means that each of them have the individual goals. Similar situations happen in financial markets, electric vehicle charging, social networks, and so on. So graphon mean-field games are a very good model for such large-scale network strategic interactions. In these games, we assume there are n number of homogeneous selfish players where the number n goes to infinity. And these interactions are captured in an asymptotically infinite network graph represented by a graphon. So the graphon W is a mapping from 0, 1 squared to 0, 1. And this is a generative model for a large random graph, such that this W consists of a function g of alpha comma beta. So for every value of alpha and beta in 0, 1, you generate a value g of alpha comma beta, which represents the probability of connection between alpha and beta. So each player alpha in our graphon mean field game model observes a private type xt of alpha in some state x, a graphon mean field population state mu t of g, and takes an action at of alpha. Based on these, it receives a reward r, which is a function of xt of alpha, at of alpha, and the mean field population state mu t of g. The graphon mean field population state mu t of g is an ensemble of the mean field population distributions mu t of alpha, where mu t of alpha is a mean field population state corresponding to each agent alpha. So each agent alpha has an associated mean field that it observes in its neighborhood, and the whole ensemble of the mu t of alpha we call mu t of g. And of course, every mu t of alpha is corresponds to a distribution, so it always sums up to 1. Now, player alpha's type evolves through a control Markov process where it depends on the next state depends on the previous state, action, and mu t of g, and the graphon g alpha. And we also have an additive noise wt of alpha, which is assumed to be mutually independent across players and across time. Equivalently, we assume that xt of alpha can be updated through this kernel given in equation number 3. Each player wants to maximize its total expected discounted reward over a time horizon t, which is given in equation number 4. Now, I want to talk a little bit about graphon mean field equilibria solution concept. And it consists of two things: sequential rationality and Fokker-Planck equation. By sequential rationality, I mean that if I'm given a graphon mean field trajectory mu g of t from time 1 to capital T, then given this mean field population trajectory, at each history, no player wants to unilaterally deviate. This is the notion when I say that given this mu g, the population mean field population mu g, sigma tilde strategy satisfies the sequential rationality. So based on this, I define a mapping phi of mu g, where I say phi of mu g is the set of all strategies of the players where sigma satisfy the sequential rationality given mu g. Conversely, I define another mapping lambda, which maps the space of strategies to the space of mu g's, where given a set of strategies sigma, I the population state mu g evolves according to the Fokker-Planck equation given in equation 7. Now, based on these two concepts, we define a pair sigma and mu g as a graphon mean field equilibrium if the strategy sigma satisfies a sequential rationality, which is phi of mu g, and the mu g evolves according to the Fokker-Planck equation mu g, which is lambda of sigma. So throughout this talk, we're going to assume Markovian strategies of the players such that they only depend on the current mean field population state mu g of t and the current state xt of alpha. And another way of writing this strategy sigma is as follows. We assume that we take actions at of alpha as gamma t operated on xt of alpha, where gamma t itself is a function that is output by a strategy theta t, which is operated on mu t of g. So one can show that this is just an alternate way of writing the strategy sigma t, and from every sigma t one can find this strategy theta t, and for every theta t there exists a sigma t. So there's a one-to-one mapping. So for any given strategy gamma t, we can define the Fokker-Planck-Kolmogorov equation as equation number 9, which succinctly we will write it as some function phi, where we are abusing the notation phi. So we can say that mu t plus 1 of g is equal to phi of mu t of g and gamma t. So the mean field population state only depends on the previous state and the partial strategy is gamma t. Now, based on this, we are going to give an algorithm to find the graphon mean field equilibrium as follows. So for every mu t plus 1 of g and xt plus 1, we define the terminal reward to go as 0. And for each time t in a backward recursive way, and for each mu t of g, we find the equilibrium gamma tilde t by solving the equation 12, where the solution gamma tilde t appears on the left hand side and also on the right hand side in the update of the mean field population mu t of g. So this is a unique fixed point equation that allows us to decompose this problem across time. So by solving this unique fixed point equation 12 for every mean field population state mu t of g, we compute the optimal gamma tilde t. And then we plug in this gamma tilde t back into the equation to find the reward to go at time t, which is v of t. And finally, when we do the whole procedure, we can define the equilibrium strategy sigma tilde t as gamma tilde t operated at xt, where gamma tilde t is equal to the theta t, which is the equilibrium generating function operated at mu t of g. Now, this is our main result where we show that the strategy sigma tilde that we just computed is actually a GMFE of the game, which means that for every, rather I should say sigma tilde and mu t of g. Mu g, which is constructed, is a GMFE of the game where given the mu g's, sigma tilde satisfies the sequential rationality condition, which is equation 15, and the mu g's evolve according to the Fokker-Planck equation, which is equation number 16. Furthermore, we show that every mean field equilibria can be found out through this procedure. So this is this theorem. Now we talk about the existence of the fixed point. So remember that in the backward recursion, at each time we have to solve this equation, fixed point equation 12. So I want to talk about the existence of the fixed point equation number 12. So there are 5 assumptions that are made in the paper by Keynes and Huang in 2018, where they show that if these 5 conditions, assumption A1 to A5 are satisfied, which are the assumptions on the update kernel of the state and the reward process, if these assumptions A1 to A5 are satisfied, then we show that there exists a solution to the fixed point equation 12 for every t. And under these conditions, it has been shown that there always exists a GMFE of the game. And since we have already shown that all the GMFEs can be found using our backward recursion, it means that for each time t, there exists a solution for the fixed point equation 12 under these assumptions. Finally, I want to talk a little bit about a numerical example. So we consider a discretized version of a malware problem where suppose there are a large number of cyber physical nodes, and each node has a private state xt of alpha, which could be either 0 or 1, where 0 represents a healthy state and 1 represents an infected state. Each node can take an action at of alpha, which belongs to 0, 1, where at of alpha is equal to 0 means do nothing, and at of alpha is equal to 1 means repair. And then the dynamics of the state evolves is given by equation number 18. And so which means that it can a state can go from healthy to infected with some probability WT of alpha, where WT of alpha is given by 19, which depends on the underlying graph form. If a node doesn't do anything, it can get infected with a certain probability. However, if it takes a repair action, it can come back to the healthy state. And each node gets an instantaneous reward R, which is given in 12, where the first term represents the risk of being infected, and the second terms represent the cost of the repair. So we consider 4 different graphons, which are fully connected graphon, Edoshveni, stochastic block model, and random geometric graphs. I won't have time to go through this definitions, but we can imagine what these are. And given these, we find the graphon mean field equilibrium strategies, which turn out to be pure strategies in this case, and they are specifically threshold kind of policies for the fully connected graph and Edoshveni, and they don't take the repair action with probability 1 for the stochastic block model and the random geometric graphs. This is the mean field update function. This is how the how mean fields are updated. And finally, this is how the mean field converges to the equilibrium mean field population state. So I would like to conclude by saying that there are certain future extensions one can consider, which is like we can consider an extension to the infinite horizon case. One can also think about graphon team optimal control problem. And there are a lot of applications that one can study, for example, population dynamics, epidemic models, and social learning, smart grids, energy and financial market using this procedure. So with this, I would like to conclude, and I'll be happy to take any questions.